Hello, here's chapter 8. We're not going to cover the whole chapter. I'll just go through kind of generally what we're going to go through in chapter. First, we have systems of linear equations and problem solving. Section 1, we're going to talk about systems of two variables right here, solving by substitution in section 2. And then we're going to connect some concepts where we're solving applications that have actually systems in this. This is probably one place in algebra where we finally get to a point where we can take a little more complex real-world situation and apply algebra and find solutions through that. The last section is systems with three variables, and we're going to go through a couple of things. We're going to end right with the mid-chapter review right here, okay? And we'll have a review assignment. I've already put the assignments on my math labs, and do a quiz right there, and the chapter test will just cover these four sections, so it'll be a short chapter, a nice chance to get a heavily portion of your grade addressed with these a shorter amount of information. So chapter 8. First section we're going to go through is systems of equations with two variables. And the first thing they do is review on translation from algebra to, from English to algebra. And what these equations can form from the text in a word problem in this case. So let's look at this first example where they're talking about an endangered species. And in 2012, there were 92 species of birds in the United States that were considered threatened or likely to become endangered. That was what they mean by threatened or endangered, and in danger of becoming extinct. The number of species considered threatened was 3 less than 1/4 of the number considered endangered. When we write systems of equations for this, we're going to translate those into expressions. In fact, we've done this in review with chapter, I think it's chapter 3. They did some of this, and it actually was more complicated because we had to basically try to write it with one equation. But there's actually two different things that are being described here that we are going to use as variables. So first thing, and this is a good step-by-step on any word problems. First, we want to familiarize ourselves with it. And what I call usually is define variables. So we let T represent the number of threatened birds, and you try to take a variable that'll remind you what that means. And D is endangered. I don't know where they get D. Maybe use E, but that's not used very often because E represents an actual irrational number, so they say D in this case. So we define the variables. What are the things we don't know? A lot of times what are they going to ask us for, or what are the answers they're asking in this, or that they want to get out of this problem. A lot of times that'll be your definition of your variable. In this case, there's two things. We have endangered and threatened species. So when we translate, there are two statements to translate. First, we look for the total number of endangered or threatened species of birds. Rewording it says the number of threatened species is T, and plus the number of endangered, they represented with the variable D, is equal to 92. Well, that creates an equation. We have T plus D equals 92. The second statement to find out of this is, they talk about a relationship between these things. Is that we can say the number of threatened species was 3 less than 1/4 of the number of endangered species. Remember, you be careful with that less than, or anytime you end up with subtraction, you got to make sure it's in the right order. I'll do things like 3 less than 5. How would you write that? It would be 5 minus 3, to remind myself that I'm going to take this 1/4 the number of represents multiplication, and subtract the 3. Well, now I have two equations that are related to each other. And with this information, I can then hopefully solve this and find out what each variable is equal to. And that's what they're introducing here in this chapter, is that when I have systems, if I have two equations with two variables, I can get solutions from that. Where before, if I just had two variables in one equation, I have, if it's linear, I have an infinity of solutions. But they really want to get specific here, is that we want to know what it is for this specific example. So they don't even solve that in that example, but they're showing how to translate that into equations, which should be a review. And then they talk about it here. A system of equations is a set of two or more equations in two or more variables for which a common solution is sought. So what is a solution again? It is the numbers that I can substitute into that equation and make it true. Well, like I said, linear equations, there's an infinity of them. There's a relationship between the ordered pairs and it draws a line. Well, in systems, there can be, not always, but there can be a single solution that works for both of those, and that's what we're usually looking for. In this example too, they basically translate this. Again, I'm not going to read through the whole thing, but I want to point out this tool of a table, which can be really nice to organize your stuff. Put in, first of all, you still need to define your variables. Put in a letter for the things that are unknown. So they have number bought, they don't know how many silvers were bought or gemstones were bought, but they do know the total, okay, which is 80. Now, this alone, again, just to illustrate what we've gone through in the past, well, if I got 10 silver, I would have to get 70 gemstone ones, and so on. But I could keep doing that forever. I could say 1 and 79 and so on. Well, they did give us the prices, and the prices basically is related to the number of silver ones at 40 cents a piece. So how would I write an expression for that? Well, it would be, if I'm going to do it in cents, it would be 40s represents the price you would pay for any number of silver ones, and 65 cents for the gemstone ones. So they organize it in this way, which sets up these other expressions, which I know because they told me how much actual money I spent. I can set up another addition of those expressions that will add up to this total cost. So we have a system here. Here's two equations that we can set up. Now they go back through, this is again review, but we're setting it up, and we're going to make sure you have an understanding of the tools that you need to have to get through these systems. Well, a solution of a system of two equations and a variable is an ordered pair, a relationship between those two numbers that make both equations true. Well, I could say, what's a solution? Well, the definition of a solution is a number, if it's one variable, that makes that equation true. Well, this is the same thing. So when we say we have two equations and we want a solution, it has to work in both equations and make both of those true, which means that both sides would be equal. So that's what they do in this case, is they test. They want to know, it says determine whether this ordered pair, -4, 7, is a solution to the system. Now, if they didn't use x and y, which they do here, this first value is x and the second value is y, or in a situation where a graph, this first number will represent movement on a horizontal plane, or left, right, and the second number will be vertical or up and down. So we have these two equations. They put in the values for each. So in this first one, x plus y equals 3, they put in -4 for x and 7 in for y. And yes, it is makes that true. Negative 4 plus 7 does equal 3. And in this case, with this equation here, they do the same thing. They put negative 4 in for x. Make sure you follow order of operations. And 7 in here, and they end up with negative 27 equals negative 27. Well, that's true. So what we've determined, because it makes both equations true, this ordered pair is a solution to that system. Now the next thing they're going to show us basically is, I've never seen an engineer in the field or somebody working on a mathematics problem say, well, let's graph this and see what a solution is. But it's really important to understand visually how these things can fall together. That's probably the biggest asset to graphing. And if we have two linear equations like these ones that we just went through here to see if that solution is there, if I graphed each one of these, where here is this blue line represents all the solutions, remember this is an infinity of points that follow this straight pattern here, is a line, right? Well, there's an infinity of solutions on this blue line where x plus y equals 3. I can take any ordered pair on that blue line and it'll make this true. Well, the red line here represents all the ordered pairs that make this equation true. Well, what has to happen for them to have a common solution is that there has to be, especially if one common solution, there has to be a point of intersection, and where these two lines do, there is exactly one ordered pair that is shared by both of these lines, and that is the common or the solution to this system. So we could graph things and find out approximately where this ordered pair of intersection could be, and that's what they go through this examples and do that. So they graph these, they make graphs out of that. Hopefully you might have to look and remind yourself about that. I like to use the slope-intercept form. A lot of times it's the fastest way to graph. This is standard form stuff where you can just put in values and get ordered pairs, and you can use your graphing tool on MyMathLabs and get those. Well, let's look at B here. When we graph equations, if the lines have the same slope, in this case negative 3, and different y-intercepts, in other words they are different lines, they cross the y-axis at different points, but they have exactly the same slope, they are parallel. Now if I look at this and I have these two equations, is there a solution for this system? In other words, is there an ordered pair that will make this true and this true at the same time? And there is not. There's never any point of intersection, so there's no point where they will have a solution. So in this case, it's very possible, if you have parallel lines, that it'll create a situation where there's no solution. Another situation that can happen is you can have lines with the same slope and the same intercept, or in other words, they basically lie right over the top of each other, and all the ordered pairs that work in this one also work in this one. So there can also be an infinity of solutions. So you could pull out a point, and say, hey, I think the y-intercept is here, which is this part here, and substitute it in. You say, hey, it makes this true, and then you put it in this one, it makes it true. Well, that is a solution, but you got to be careful is that if in this situation there's an infinity of ordered pairs. So the only way we can show infinity when we're answering things, we have to use set notation. Now notice here, right here, this is set notation again. Get familiar with this. How I'd read this is the set of the ordered pair xy, or the ordered pair xy, such that pipe symbol, that 3y minus 2x is equal to 6. Now I could have also said it is the set of ordered pairs for x, y, or the ordered pair x, such that I could use this equation too, because that has the same ordered pairs. Usually you try to take the easier or the more simplified one. This just has smaller numbers, I guess is why they choose that. So when we go through this stuff here, there are three things that can happen, and they put some terminology in here to lock on, or hopefully do that. If we have something that is consistent, we say there is at least one solution. If it's inconsistent, it means that there's absolutely no solution. So if it's we have a system of two linear equations, then it would mean that they're parallel and they don't lie over the top of each other. There are other situations that could occur that are not parallel if we use nonlinear equations and stuff. But this type of system is inconsistent. In other words, there's no solution for this system. And then lines that coincide, basically this definition they gave us, it says at least one solution. Well, if they lay over the top of each other, if I have an infinity of solutions, they are consistent. It has at least one deal. They're just pointing out the three different situations that happen with linear equation. What do we call those? So these two are consistent, and no solution is inconsistent. When one equation in a system can be attained by multiplying both sides of the equation by a constant, the two equations are said to be dependent. Thus, the equations in example 4c are dependent, and those in 4a and b are independent. These systems are of three or more equations, the definitions of dependent will slightly modify. So they're throwing some more terminology in here. Here is a nice little graphic here and explains this stuff. Graphs that intersect at one point, they are consistent because they have at least one solution. And since neither equation is multiplied a multiple of the other, they are independent. When I have parallel, they are inconsistent because there is no solution. But since the equation is neither equation is a multiple of the other, the equations are independent. And in this case right here, I could get exactly the same thing by multiplying this equation by -8 or -4, excuse me, right? If I took this equation and multiplied both sides by -4, I'd get this. Well, they're consistent because there is at least one solution. There's an infinity of solutions, really. But since one equation is a multiply of the others, the equations are dependent. Just to get a grasp on that. So good luck on your assignment, and more to come.